for sure is that the work done on these two guys is the same. But the question is, what is different? What is different? The difference is the rate at the way this thing is done. And that rate we call power, okay? Right, you guys, when you do exercise, you put more power, right? So you're running, more power, you know. You can run 1 meter, well no, 1 kilometer, it's very slow pace, right? Or you can run really fast, right? You put more power on it, right? So how do we calculate power? We divide the work done by the time, okay? So this one takes 3 seconds. The work done is mgh, is the potential energy. So that's 1,960 divided by 3 is 653. And this one is 1 second, so it's the same value, right? So
Professor, you said that equation for power is work divided by time?
yes.
Okay.
So another thing about force and displacement is that force can be positive, can be negative, and can be zero, right? So if this is an example of a positive work, so I'm going in the same direction, right? Now, if the theta value is 180 degrees, right, from the direction of the motion, so that is going to be a negative work, right? Can you guys imagine a situation, something we already studied, of a force that can produce negative work? A force that is opposite direction than the movement, right? If I'm moving this in this way, right? I'm applying a force, huh? Friction. Excellent. So now I'm applying a force in this direction, but it's not letting me go as fast as I wanted because there is friction, so there is work against, right? That is reducing the possible work that I could have if there were not friction, right? So that is an example of a negative work. So if there is a question on the exam, give examples of a negative work. What kind of force would be that? Friction is one. So could be an incline that I have, a block moving down, and you have friction here. So the gravity is going to produce some work, but the friction is against it, right? So how to calculate that? So I'm going to give one example here of a problem involving power. have a car. The car is initially at rest, has mass of 1,000 kilos, and and some energy is given to the car, and go to a final velocity of 5 meters per second. So what would be the power here? So first you need to calculate the kinetic energy before and after, but after is 0. So power is going to be the work done, that is the kinetic energy, divided by the time. And this was like 2 seconds. A force was applied here for 2 seconds and gained some kinetic energy. So you calculate the kinetic energy divided by the time, and this is going to give you 6,250 watts. So joule per second, because energy is joule, and this is second, so joule per second is watts, okay, W. So potential energy is could be the energy caused by gravity, mgh. Mg is force times h is distance, right? So this is potential energy. Another kind of potential energy is the elastic potential energy of a spring. So what is two things that are similar between these two forms of potential energy is that they depend on the distance, okay? They depend on the distance, on the position. So if I have a spring with a block here, and I bring this block up to here, so now the spring has built some energy that is going to tend to bring this back here, right? Right? It's the return. I apply a force here, I change this position to this one here, and now has potential energy that is going to try to bring this back. The same gravity. I have this thing on the ground, I change the position of this, and now it has gained potential energy. So how do they gain potential energy? Is by moving this, right? Changing the position. Okay? So this kind of energy, we call that conservative. Okay? So let's do a problem now. So now I have the block has an initial velocity of 12 meters per hour. So I have an angle here of 35 degrees. The height here is 2.5 meters, that's h. And I'd like to know what is the final velocity. Okay. There is a frequency, kinetic friction coefficient of 0.0800. That's the coefficient of friction, of kinetic friction. This block is moving up, there will be a friction there. So let's draw here the block on the incline. So we have the weight, mg. Because it's moving up, the friction force is going down. And here I have my theta, right? And I have here a V, and here my normal force. So to calculate the friction force, I need to multiply times the normal and the coefficient. In order to calculate the normal, I need to know this projection here, the projection of the gravitational force on this axis, and that is going to be what? What's going to be the projection of mg on this axis? Huh? Yeah, mg cosine theta. So n is going to be mg cosine theta times the coefficient there. Okay? Now we need to know this value here, right? We need to know this distance. So how do I calculate the distance? Well, this distance is going to be sine 35, it's going to be 2.5 divided by d. So I could calculate the distance that way, all right? Now, we have two things going on here. One is the force of gravity. That is a conservative force that depends on the position, right? And the other one is the friction, right? It's going to cause, it's not conservative, okay? So what does that mean in terms of mechanical energy, conservation of mechanical energy? The initial kinetic energy, if there were no friction here, the initial kinetic energy would be converted into a potential energy here, right? You guys agree with me? Right? Would be completely converted there, and then the extra would be related to this kinetic energy here. So let's write down the kinetic energy initial, I'm going to call KEI, plus the potential energy initial is going to be equal to the kinetic energy final plus the potential energy final. if this is a completely conservative system, this is what's going to happen, right? But we have some work here that is not conservative. That is caused by this force of friction, right? Now, how much is that work? Is the force of friction that we're going to calculate here times this distance that we can calculate here. All right? So let's do that. But because this is not conservative, I need to add this work for friction here on this side. Right? That is taking away from here. What is the initial potential energy at this point? This is on the ground. Where is the potential energy here? Zero, right? This is 0. So I can write down that mvi squared is going to be equal to mv final squared plus mgh plus this work. And this work is going to be F, right? That is mg cosine theta times the coefficient of friction times d. But d is 2.5 divided by sine of 35. When you plug in all these values, you're going to find that Vf is 9.6 meters per second. Okay? So, do you understand the problem? What's happening here? Okay, let's talk about this. So I have this ball, I have this height. What is the potential energy at this point? Is mg, right? M, the mass of this ball, times this height. Okay? So, what is the kinetic energy right here, right now? 0. Everything it has is potential energy. When I let it go, it converts, it starts losing potential energy with the height, because the potential energy at this point and at this point is different. This is higher than this one. When it comes to this point, it has converted this difference into kinetic energy until it goes to the ground, where the ground potential energy is completely 0, has converted everything that we have into kinetic energy. So this is a conservative system, a conservative problem, that the initial kinetic plus potential energy would be equal to the final kinetic and potential energy. All right? Now, this problem here has a force that is not conservative, that does not depend on position. Friction does not depend on the position, right? And friction is, you cannot recover. The work done by friction is lost in heat, is lost in sound. Potential energy we can recover. And because we can recover, we call that conservative. The work we do on the spring, if we move from one position to another one, and if we let it go, we can recover that work, right? But friction here is lost. So it has to go somewhere. So it's breaking this balance here, so I need to add that here, right? if I had no friction, what would be the value of the final speed? Would be the same, less, or higher than what we found?
Would be a little higher.
Huh? Would be higher, right? Exactly. Would be higher.
What did you use for mass?
What I use for mass?
Yeah.
I didn't write that down. Let's see. Mass is 60 kilograms.
Okay.
Yeah, you can check that on my notes, the calculations and everything on my notes. Okay? All right? So let's have a break, and when we come back, we finish the experiment from last class.
Professor, on this equation, you did miles per hour. Does it matter? Do we have to convert it to seconds?
Did you show?
Oh,